Hello everybody. Today I am starting module 2 and this is my first lecture. In the last week I discussed the plate theory and the different assumptions required for analyzing of plate. We basically concentrate on the thin plate with a small deflection, and then we have derived the differential equation of equilibrium of the plate. The fourth order differential equations of the equilibrium of the plate has been derived, and it has to be solved for given loading conditions and boundary conditions in the plate. The plate may have any geometrical shape and boundary conditions may also be different, but the exact solution of the governing differential equation of the plate that we have derived in the last class cannot be achieved in all such cases. Very few cases the analytical solutions are available, but these analytical solutions provide a benchmark result, and it is also used as a auxiliary result in other numerical problems that you require to solve the complicated plate problem. So, today I will discuss a method for rectangular plate that has been developed by Navier, and with the help of this method we will try to find out the exact solution of the differential equation. Okay. So, the Navier's method that I have told you, this has been developed by Navier and it is applicable for plates simply supported along all edges, and it is specially applicable for rectangular plate. So, today I will discuss the Navier's method for uniformly distributed load and also partially covered load. Okay. So, let us see the governing differential equation for the plate. The governing differential equation for the plate is given as del 4 W equal to Q by D, where D is the flexural rigidity of the plate, and if the thickness of the plate is uniform, we can assume that D is a constant and it is given as E h cube divided by 12 1 minus mu square, where h is the thickness of the plate, E is the modulus of elasticity of the plate material, and mu is the Poisson ratio. You can see here this is a fourth order partial differential equations, and it is also a non-homogeneous equation, non-homogeneous differential equation. So, if I consider the linear analysis, then I have to obtain the solution in two stages. First, I have to obtain the homogeneous solution taking the forcing function as 0, and then I have to obtain this particular integral or particular solution, and then superimposition of that will give you the general solution. The process becomes lengthy if we follow this the conventional rule of solution of the differential equation, but Navier has overcome this difficulty by using a double trigonometric series. The double trigonometric series that he proposed is only applicable, that its validity is only for rectangular plate having 4 edges as simply supported. Now, here del 4 is the operator which is given by del 4 divided by del x 4 plus 2 del 4 del x square del y square plus del 4 divided by del y to the power 4. Okay. We consider a simply supported plate, length is A and breadth is B. Okay. Now, here you can see that the boundary condition for simply supported is written here as equation 1, 2, 3, 4. So, let us see what are their implications. So, at x is equal to 0, say this edge, we see that for simply supported condition deflection is 0 and bending moment has to be 0. Now, bending moment equation, you know, it is given by minus d into del square w del x square plus mu into del square w by del y square. Now, since bending moment is 0 here and bending moment contains curvature in two direction in general. Now, here you can see this edge is supported along this edge x is equal to 0 edge, that is along the y axis. So, there cannot be any curvature along the y axis at this edge. So, therefore, second term del square w del y square, which is multiplied by mu, does not exist. Hence, the condition for boundary at this edge x is equal to 0 becomes w is equal to 0 del square w by del x square. Similarly, at x is equal to a, just opposite edge, you can see that deflection is 0, obviously it is supported. So, deflection is 0 and the bending moment del square w del x square plus mu into del square w del y square is 0, but since it is supported all along the edges, del square w by del y square is 0. So, the condition becomes simply del square w del x square 0. If we go other two edges, say y is equal to 0 edge, this edge. Now, here w is 0 and similarly we get del square w by del y square is 0, because here the edge is supported all along the edge which is parallel to the x axis. So, there cannot be any curvature along the x axis. So, therefore, the term that only exists in boundary bending moment equation is del square w by del y square. So, it is 0 because bending moment is 0, this edge permits rotation because it is simply supported n. On the opposite edges where y is equal to b, again deflection is 0 and del square w del y square is 0. Now, we have got this condition, mainly the condition is deflection and its second derivative. So, deflection function and its second derivative along x and along y direction need to be 0 along the edges, since these edges are simply supported. So, Navier has proposed, say for such type of condition, a double trigonometric series is the most suitable one for the solution of the differential equation. So, this equation you can see w is equal to double sum a m n sin m pi x by a sin n pi y by b, where a m and n are integers and this is a infinite series. So, summation index m varies from 1 to infinity, similarly n varies from 1 to infinity. This series that you are seeing is popularly known as Navier series and it satisfies the boundary condition. You can see the boundary condition requires w is equal to 0 at x is equal to 0 at x is equal to a, and also w is 0 at y is equal to 0, y is equal to b. So, therefore, if you put x is equal to 0 here, deflection becomes 0. If you put this x is equal to a, then sin m pi, that is of course, m for any integral value of m, this sin m pi will be 0. So, therefore, deflection condition is satisfied, and if you go to satisfy the bending moment condition, you differentiate this expression 2 times with respect to x as well as with respect to y. So, if you see that if the satisfaction of boundary condition specially for bending moment along x direction requires that curvature along the x direction, that is del square w by del x square equal to 0. So, if you take the second derivative of this equation, then obviously that m pi m square pi square by s square term will come, and again this sign function will appear with a proper sign. Okay. So, again this boundary, this condition del square w by del x square is satisfied. Similarly, if I differentiate this expression 2 times with respect to y, I will come back again this sign function sin n pi y by b. Of course, this coefficient n square pi square by b square will come out. Now, put y is equal to 0 or y is equal to b, this bending moment condition will be satisfied. That means, curvature will be 0. So, bending moment condition will be satisfied. So, this Navier series proposed as a trigonometrical series, that is a double trigonometric series, completely satisfy the simply supported boundary condition. It is very well known series and it gives the value of deflection and other stress resultant, the converged value of this deflection and stress resultant very rapidly. Of course, if you go the stress resultant with a higher derivatives, the convergence may be slow, but within a say maximum say 5 to 7 terms, you will get the convergence within the acceptable limit. Now, most important thing is the coefficient AMN. Coefficient AMN is still unknown. That coefficient, if I find out, then I will get the complete deflection, that is the deflection completely. That means, AMN is still unknown. How it can be found? Now, since it is a solution of the differential equation, we take it as a solution of the differential equation and it satisfies the boundary conditions completely. So, if it is the solution, then it should satisfy the differential equation also. So, substituting this series now in the differential equation, we have to obtain the AMN. Now, how the deflection will take place in this simply supported plate? Let us see the functions, the sin m pi x by a and sin n pi y by a. These are waves and we call it half waves, because this ranges from 0 to a and 0 to b. Now, m and n are integers. Now, you can see that for m is equal to 1 along the length direction, the first half wave is this. Second half wave, when we take m is equal to 2, we get this second half wave. Similarly, if you consider m is equal to 3, you will get the third half wave. Like that, your number of half waves will increase as you increase the integer. So, similarly, in the width direction, you will get the half wave, which is the width direction, the function is sin n pi y by b. So, if you put n is equal to 1, you will get 1 half wave. If you put n is equal to 2, you will get 2 half wave, and so on. So, what is the Navier solution? The Navier solution is product of 2 half waves and their summation. Okay. So, superimposition of this, the product of 2 half waves, and if you summed it, then you will get the deflected surface. A typical plot of the deflected surface of a simply supported plate looks like that. When you superimpose all the waves and if you know the AMN correctly, then you will get the correct magnitude of the deflection function or deflection surface of the rectangular plate simply supported along all edges, subjected to any type of load here. Now, let us come to the solution. So, W is equal to double sum AMN sin m pi x by a sin n pi y by b. So, two terms you are seeing it. Now, if you expand this, you can write it, say first term will be a 1 sin pi x by a sin pi y by b. This is first term, you can call it a generic term. Then second term is say m is equal to 1, n is equal to 2, a 1 2 sin pi x by a sin 2 pi y by b. Third term m is equal to 1 and n is equal to 3, you will get sin pi x by a sin 3 pi y by b, and so on. So, you will get a infinite series. So, if you take the second derivative of this, which we require to calculate bending moment also, if the deflection is completely known, then after taking second derivative with respect to x, you will get minus a 1 pi square by a square sin pi x by a sin pi y by b. Similarly, here you will get minus a 1 2 pi square by a square sin pi x by a sin 2 pi y by b, like that, because we are taking this derivative with respect to x. Similarly, derivative with respect to y, we get minus a 1 1 pi square by b square sin pi x by a sin pi y by b, and minus a 1 2, because 2 pi by b will come out. So, 4 pi square by b square sin pi x by a sin 2 pi y by b, and so on. So, this derivative function can be evaluated. So, you can see that these derivatives satisfy the condition at the edges, because bending moments have to be 0 in the respective edges. Now, we have to differentiate it up to fourth order, because the differential equation is a fourth order equation. So, after differentiating this w 4 times, we will get del 4 w del x by del x 4, and differentiating w with respect to y 4 times, we will get del 4 w by del y to the power 4. Then with middle term, there is del to the power 4 w divided by del x square del y square and multiplied by 2, this term is obtained. It can be easily verified that when we differentiate w with respect to x 4 times, we will get m to the power 4 pi to the power 4 a to the power 4 as a constant term that will coming out as a process of differentiation. Okay. But the function, that is sin m pi x by a and sin pi y by b, will remain unchanged, because it is a even number of derivatives. Then here also it is first we differentiate 2 times with respect to x, and then the result is differentiated 2 times with respect to y. So, again it is a even number of derivatives, and the function remain as it is, because there will be no change of sine function, only the coefficients that will be changed. So, coefficient here we are getting m to the power 4 pi to the power 4 by a to the power 4 plus, due to differentiation of this quantity w with respect to x 2 times, and the result is again differentiated with respect to y 2 times, we will get the coefficient 2 into m square n square pi to the power 4 divided by s square into b square. So, the coefficients are plugged in here, and the function remains as sin m pi x by a into sin n pi y by b, and the right hand side remains as it is q x y by d, and it is under summation because a m n is there. So, double sum is written here. Okay. Now, we want to find out, our target is to find the a m n. So, a m n can be found out by expressing the load q x y as a Fourier series, and then taking a general term and comparing the coefficients of like term, we can find the a m n. So, I will illustrate the process from the first principle. Okay. So, this function or this constant that is written inside the second bracket m to the power 4 pi to the power 4 by a to the power 4 plus 2 into m square n square pi to the power 4 divided by a square into b square plus n to the power 4 pi to the power 4 divided by b square can be conveniently expressed as m square pi square by a square plus n square pi square by b square whole square. So, that is obvious from this equation quantity. Then this function is written here sin m pi x by a sin n pi y by b, and right hand side is the loading function q x y divided by d. This loading is here a distributed loading, that means q is also a continuous function of x and y. Now, multiply both sides of the above equation this equation by sin m dashed pi x by a into sin n dashed pi y by b, where m dashed n dashed are integers, m and n are also integer, and m dashed n dashed are also integers. So, we have taken different symbols with the intention to use this some well known principle of this mathematics or sign series. So, therefore, we have used this symbol integer, the m and n integer with a different sign symbol m prime and n prime. So, if I multiply both sides by this function, I am writing this left hand side which was this a m n m square pi square by a square plus n square pi square by b square sin m pi x by a sin n pi y by b multiplied by this function sin m dash pi x by a sin n dash pi y by b. Of course, this quantity is under summation. So, summation is with respect to m as well as with respect to n, it is a double sum, and right hand side is q x y by d, and due to multiplication of both sides with this quantity, that is sin m dash pi x by a sin n dash pi y by b, we also write sin m dash pi x by a sin n dash pi y by b in the right hand side. Okay. Now, integrate. Next step is to integrate both sides in the domain of the plate. So, I integrated the equation that we have obtained in the last slide, this equation with respect to x and y, and the limit is 0 to a and 0 to b. We have taken the origin of the coordinate system as one of the corners of the plate. I have taken in the left hand side top corner of the plate. So, this x along x direction, the range of x is 0 to a, and along y direction the range is 0 to b. Okay. So, we put the limit 0 is the lower limit of the integration with respect to x, a is the upper limit of the integration with respect to x. Similarly, here 0 is the lower limit for integration with respect to x y, and b is the upper limit for integration with respect to y. Okay. So, we have written the limit, now we can integrate it. So, we plucked the x term together and then try to integrate with respect to x. Similarly, we pluck this y term, that is sin n pi y by b and sin n dash pi y by b, and then try to integrate with respect to y. Okay. The right hand side there is no problem, there is no sum. So, we write q into sin m dash pi x by a sin n dash pi y by b dx dy, where m dash n dash are integer. Whether you put here m or m dash or n or n dash, it does not matter, make any difference. Okay. So, here this equation can be simplified. Okay. This equation, if I number it by 4 as a 4, say equation number 4 here, it can be simplified by using orthogonality condition. So, orthogonality condition of the sine function is well known, and it is sin m pi x by a sin m dash pi x by a dx 0 to a. So, if I integrate this, then for m is equal to m dash, the value of the integral is a by 2, and for other values of m and m dash which is not equal to each other, that is m is not equal to m dash, we get 0. So, this is one condition. Similarly, along the y direction, when I integrate the function with respect to y with a limit 0 to b, we get b by 2 for n is equal to n dash, and 0 if n is equal to n is not equal to n dash. So, using this property, now it can be seen that all the terms containing the sin m pi x and sin m dash pi x by a, sin m pi x by a into sin m dash pi x by a, where m and m are different, will be vanishing. Similarly, all the terms in the summation with sin n pi y by b into sin n dash pi y by b with a condition that n is equal to not n dash again will vanish. So, ultimately we will be left over only with the term to be integrated, that sin square m pi x by a dx into sin square n pi y by b integration with respect to y and limit 0 to b. So, two integrations are needed now here for m is equal to m dash and n is equal to n dash, and obviously the result will be a by 2 into b by 2. So, here now we can write, because summation term is now not required, because the only terms that is remaining is m is equal to m dash and n is equal to n dash. Other terms will be 0 because of orthogonality condition. So, that property, orthogonality property, is the key point here. So, without this orthogonality property, this Navier method cannot be formulated. So, orthogonality property of the sine functions is utilized here, and then we get a m n coefficient as a m n into m square pi square by a square plus n square pi square by b square whole square a b by 4. A b by 4 has come here, this term has come here due to product of a by 2 and b by 2 as a result of integration of sin square m pi x by a dx and into integration of 0 to b sin square n pi y by b dy. So, as a result of this you get here a b by 4. Right hand side remain as it is 1 by d integration, of course 0 to a 0 to b, that integration is not completed, it depends on the nature of the function q x y, then only you can integrate. So, q x y is here and the term sin m pi x by a sin n pi y by b dx dy is here. So, m and n are integers. Now, from this equation, now it is possible to write a m n, the coefficient of the deflected series or deflected function, deflected surface, whatever you call, is a m n equal to 4 q m n divided by d a b pi to the power 4 m square by s square plus n square by b square whole square. How this term has come? Because this integral is taken as q m n, and this is say pi square is taken out. So, it becomes pi to the power 4 and a b is there and 4 is there. So, if this term is q m n, then we can write a m n as 4 q m n d a b pi to the power 4 into m square by s square plus n square by b square whole square. Okay. Now, q m n here remains to be determined. You can see q m n can only be determined when you know the load function. So, given the loading condition in the plate, it may be uniformly distributed load, it may be uniformly varying load, or it may be any other variation of load which may not follow the linear pattern, and it may be partially distributed load. So, all this kind of load can be incorporated here. Okay. So, q x y is the loading function that we have to know, and then after integration of this quantity we can now find a m n. Now, once a m n is found out, your deflection is known. So, deflector surface you can completely know if you can find the a m n. Okay. So, what I see here, the important steps in the Navier's method is, first the Navier's method have to be applied only when all the edges of the plate are simply supported. So, that is the condition. Then for the given loading, you calculate the coefficient QMN. Once the QMN is known, then you calculate AMN. After knowing AMN, you can find the deflected surface. So, from the deflected surface or deflection function, you can go further to find out the slope, bending moment, shearing force, S shear, corner reaction, everything you can find after finding the deflected surface. Now, let us take an example of simply supported plate carrying uniformly distributed load. So, this is a simply supported plate which carries uniformly distributed load. Now, you can see here the section is shown along the longer direction as well as along the shorter direction. There is the length direction, there is A, and the shorter direction you can see this width B. Okay. The aspect ratio of the plate is A by B. Now, here the QXY, the loading function that we consider in the solution, is now a constant quantity which is uniformly distributed load per unit area. So, it is denoted as Q naught. So, as we have developed earlier, the solution where the AMN is nothing but 4 QMN divided by DAB pi to the power 4 into m square by s square plus n square by b square whole square. Okay. So, most important thing is to find QMN. So, QMN is now the integration of this Q naught sin m pi x by a into sin n pi y by b dx dy, and the limit of integration is 0 to a for x and 0 to b for y. Okay. You can see here that Q naught is a constant quantity. So, it can be taken outside the integral sign, and after integration with respect to x, you will get this term as a constant minus a by m pi, and the integration of sin m pi x by a will be cos m pi x by a, and this constant appears after integration, that the constant a by m pi with a minus sign comes out here, and the limit of integration is shown here as 0 to a. Similarly, for the term sin n pi y by b dy and integrated within a limit 0 to b, you will get minus b by n pi as coefficient and cos n pi y by b, and to be evaluated with a limit 0 to b. Okay. So, when we evaluate this quantity now, we get Q naught A B m n pi square, this m n are coming here, pi square is coming, and A B is there, and minus minus again plus sign will be there. Okay. And due to substitution of this upper limit and lower limit, you will now get cos m pi minus 1 and cos n pi minus 1. One interesting thing is that for any odd value, even value of m, say for m is equal to 2, this function will be 0, and for n is equal to say 2, this function will be 0. So, if m is equal to 1, n is equal to 1, then you will get this as a minus 1, that is minus 2, and here also you will get minus 2. So, ultimately the result is 4 Q naught A B, and then you are getting m n pi square, where m and n are integers. These m and n are only odd integers, so that integral value is non-zero. Otherwise, for even value of integers, that is m and n are even integers, then the integral will be 0. So, our Q m n is now 4 Q naught A B divided by m n pi square. So, once the Q m n is known, you can get A m n. So, A m n after simplification 16 Q naught divided by m n pi to the power 6 into m square by s square plus n square by b square whole square into d for m and n varying from 135 up to infinity. Okay. One interesting thing you can see here, that deflection function is evaluated for uniformly distributed load covering the entire plate only for odd harmonics. There is only odd half waves will contribute to the deflection. Okay. Q naught is the known quantity, A and B are the size of the plate, and D contains the material property as well as thickness of the plate. Okay. Now, once you know W, then you can go for calculating the other quantities. So, other quantities of interest are slope. Slope in the x direction is given by del W by del x, and it is equal to pi by A summation, and due to differentiation of this sine function, this m pi by A term will come out. So, pi by A is a constant we have taken outside the summation term, and the integer m we have kept inside this summation term. So, it is written like that, pi by A double sum m equal to 1 to infinity, n equal to 1 to infinity, and m a m n cos m pi x by A sin n pi y by B. Similarly, the slope in the y direction is calculated del W by del y equal to pi by B summation m is equal to 1 to infinity, n is equal to 1 to infinity, n a m n sin m pi x by A cos n pi y by B. Bending moment quantity has to be calculated utilizing the second derivatives. So, we write the bending moment expression as m x is equal to minus d del square W by del x square plus mu into del square W by del y square. Similarly, m y equal to minus d del square W by del y square plus mu into del square W by del x square. Twisting moment is calculated by this cross derivative del square W by del x del y, and once the deflection function is known, systematically all the derivatives can be calculated. So, for convenience I just showing you the other higher derivatives, del square W by del x square, that is minus pi square by a square term will come, and inside the summation it will be m square a m n sin m pi x by A sin n pi y by B, and it is needed for calculation of m x or m y in the both bending moment expression m x m y, these derivatives are needed. So, similarly, del square W by del y square is given by minus pi square by B square double summation m is equal to 1 to infinity, n is equal to 1 to infinity, n square a m n sin m pi x by A sin n pi y by B. This mixed derivative del square W del x del y, which is needed for calculation of this twisting moment. Twisting moment is developed in the plate. So, this twisting moment is sometimes important, and it is calculated as with the help of this derivative. Of course, it has to be multiplied by minus d into 1 minus mu. So, final result of this derivative is pi square by a b summation a m n cos m pi x by A cos n pi y by B. Okay. Shear force you need to find out. So, shear force required third derivative. So, third derivative is calculated. Again you can see this function when it is differentiated with respect to x, you will arrive the third derivative quantity, that is del cube W by del x cube equal to minus pi cube by A cube double sum m cube a m n cos m pi x by A sin n pi y by B. Because the derivative is taken with respect to x, so this term remain untouched. Okay. Similarly, del cube W by del y cube equal to minus pi cube by B cube double sum n cube a m n sin m pi x by A cos n pi y by B, and these quantities are needed for shear force calculation. Now, here see the shearing force expression. Shearing force expression is given as this minus d and del square w, which is Laplacian, del square is a Laplacian operator. Similarly, q I is also given as minus d del y by del y del square w, where del square here is a Laplacian operator. So, it is obvious from these two expressions. S shear force is also used in plate problems, because S shear has been proposed by Kirchhoff by combining this effect of twisting moment and shear force along the edges. So, he combined these two conditions to give a single quantity S shear along the x axis, along the edges which is running parallel to x axis, or along the edges which is running parallel to the y axis. Okay. So, S shear force, if you see, it will be distributed like that. So, the edge, say x y is equal to 0 edge, here you are getting the S shear force is, it is for simply supported plate, of course, it is a sine function and it is a function of x. Similarly, if you see the S shear force along, say x is equal to 0 edge, this the shear force is a function, S shear force is a function of y and it is a sine function, and the opposite edges you can also see. So, S shear force, when you integrate it, integrate this S shear force, you will get total S shear at this edge, similarly all other edges, and this S shear plus other reactions at the corner should be balanced by the vertical load or transverse load acting on the plate. Okay. So, Kirchhoff's S shear, we require this third derivative and this. So, Kirchhoff S shear is calculated, we require third derivative as well as the mixed derivative. So, all these quantities I have shown you in this slide, in the previous slide. So, that you can utilize here to calculate the S shearing force, which is very important, and along an edge parallel to x axis and along the edge parallel to y axis, the S shears are calculated. Okay. Now, let us see in an example. We take a square plate and dimension a across a, we have to find the maximum deflection and maximum bending moment for UDL. Okay. So, we take the Navier series, we have already obtained the solution, and here we take A is equal to B. Now, purpose of this problem is to find out the deflection quantity as well as to find the effect of number of terms in the series, because we are using a series. So, we have to see how it converges. So, W x y is given as the summation of this term 16 q naught a to the power 4, because A is equal to B. So, I have manipulated this such that this factor, dimension factor A only remains here. So, 16 q naught a to the power 4 divided by m n pi to the power 6 m square plus n square whole square into d sin m pi x by a sin n pi y by a, and summation is from 1 to infinity, and n is equal to 1 to infinity, m is equal to 1 to infinity, n is equal to 1 to infinity. Of course, you should only sum with the odd number of terms. So, maximum deflection occurs at the center. So, x is equal to a by 2 and y is equal to a by 2. So, when we put this x is equal to a by 2 and y is equal to a by 2, we get the maximum deflection as this. So, q naught a to the power 4 by d is a constant term, and we have taken outside the summation term, and that summation term we now have to evaluate and see how the maximum deflection converges with the number of terms. So, here m and n are odd integers, because we have seen that even integers have no contribution towards the solution for the deflection in case of simply supported plate subjected to uniformly distributed load. Okay. So, for m is equal to 1, n is equal to 1, the center deflection is calculated and it is found after substituting the value of integers. Say here both the integers are 1. So, we get the result as 00416 and this is the load and dimension and flexural rigidity. Okay. Similarly, m is equal to 3, n is equal to 1. When you increase the number of half waves in x direction, but number of half waves say in the y direction it is 1, then again we get the center deflection as this minus 5.5475 into 10 to the power minus 5 and q naught a to the power 4 divided by d. Because the integers power appears in the denominator. So, therefore, the gradually the deflected value deflection will decrease when you go in the higher number of integers. Okay. So, we have seen that considering only first term we get the deflection as 0.00416 the coefficient and other terms are there q naught a to the power 4 divided by d. When we consider the term m and n varying from 1 to 3, that is m is equal to 1, n is equal to 1, m is equal to 3, n is equal to 1, m is equal to 1, n is equal to 3 and m is equal to 3, n is equal to 3, we get W max as 0.00400606 into q naught a to the power 4 by d. So, difference between this 00416 minus 0040606, if we will evaluate and take the ratio of the improved deflection that we get after considering the higher number of terms in the summation, then we get the difference percentage difference is 2.45% only. So, first term is adequate to give a reasonable value of deflection surface of the series. So, for calculation of deflection at the center of the square plate, only first term of Navier series is adequate. But if we go for the higher quantities, higher derivatives to find the stress resultant like the bending moment, shear foot etc., then the first term may not be adequate. So, here the bending moment expression is this m x is equal to minus d del square w del x square plus mu into del square w by del y square, and after taking mu is equal to 0.3, we have taken here mu is equal to 0.3 later on. First we arrange this equation, okay, d d will get cancelled. So, maximum bending moment again will occur at the center and maximum bending moment quantity is 16 q naught a to the power 4 divided by pi to the power 6 m n m square plus n square whole square m square pi square by s square plus mu into n square pi square by s square and sin m pi by 2 sin n pi by 2. So, the maximum bending moment is written like that, and considering this number of terms, we now see how it converges. So, taking on the first term we get the coefficient of bending moment as 0.05338 and with other terms we calculate the coefficients, and then when we sum up the terms then we get the difference. So, when we take the first 4 term, that is m varying from 1 to 3, n is also varying from 1 to 3, maximum bending moment comes out to be 0.04692 coefficient, and here coefficient is 0.05338. So, percentage difference you can see here is 13.77%. That means, the percentage error in bending moment is higher compared to deflection in the Navier's method. So, more number of terms are needed to improve the accuracy. Okay. So, if you see the deflection versus aspect ratio curve, you will see that deflection increases with the aspect ratio first, and then after it does not increase much and it becomes almost same. So, with a higher aspect ratio. So, if we compute the bending moment, say I take bending moment along the x direction with b by a ratio, and we see that our Navier's solution gives a result this with a blue curve that is seen here, that is the variation of bending moment coefficient with aspect ratio. But if I take the IS code value, because our Indian standard 456 has given the bending moment coefficient for simply supported slab for different aspect ratio. So, here we can see that IS code values are slightly conservative compared to this exact method that has been used in Navier's solution. Okay. Now, let us see what is corner lifting force. Corner lifting force is a force that is generated at the corner. How it generates? You can see that torsional moment mxy dy, if we take an elemental length dy, then torsional moment mxy dy can be replaced by two equal and opposite forces. So, if we do this at the corner, this force will add up, and giving a upward reactive force. So, in the length of dy, say here, the total torsional moment mxy dy can be replaced by two equal and opposite forces mxy. Similarly, here also along the adjacent edges, the torsional moment myx, or which is equal to myx into dx, will be replaced by two equal and opposite forces mxy and and at the corner you can see these two forces are added up and the reaction is R naught. So, R naught equal to 2 mxy is the corner reaction. So, this happens in case of simply supported plate. So, if no anchorage is provided, these forces can lift up the corners. Since this condition is generally undesirable, it should be avoided by holding down the edge of a simply supported plate. For reinforced concrete slab, provisions are given in IS code for providing the corner reinforcement to prevent the lifting up of the corner. Now, let us see a simply supported plate when instead of fully covered load, a partially covered load is applied. So, again the load is uniform, having a area of alpha cross beta. So, that is the loaded area, and let us assume that the centroid of the load is located at the coordinates xi and eta. So, x coordinate is xi and y coordinates is eta for the center of the CG of the load. Okay. So, you can see the section here, it is not fully loaded. So, in that case how we will proceed? Okay. The procedure is same. Now, here the Navier's method has been taken here again to find out the exact solution, and Wxy equal to Amn sin m pi x by a sin n pi y by b. This is the deflected surface equation. Amn is this parameter 4 qmn divided by dab pi to the power 4 into m square by a square plus n square by b square whole square. Qmn here will be different, because q is not fully distributed, fully covered load. So, this q is now containing or occupying certain area of the or certain portion of the plate. Now, let us see what will be the limit of the integration. In that case, lower limit of this integration will be, instead of 0, it will start from here. So, obviously, it will be xi minus alpha by 2, and the upper limit is here. So, it will be xi plus alpha by 2. Similarly, in the y direction, the lower limit is your eta minus beta by 2, this point, and the upper limit is eta plus beta by 2. So, these limits are written here. Okay. So, only thing is that you have to evaluate in the same way by changing the limit of integration. So, limit of integration has been changed here suitably, and integration is carried out. After carrying out integration, you can see that when the limits are substituted, you are getting a function like that cos m pi by a into xi plus alpha by 2 minus cos m pi by a xi minus a by 2. Similarly, for integration with respect to y, the result will be cos n pi by b into eta plus beta by 2 minus cos n pi by b into eta minus beta by 2, and coefficients are there which are known quantity, that is q naught is known, a and b are known, m and are integers, and this pi is also known. So, using the well known trigonometric identity cos a plus b minus cos a minus b equal to minus 2 sin a sin b. So, this function, these two function can be taken as cos a plus b and cos a minus b. So, this formula can be applied, and after application of this you get q m n equal to 4 p a b divided by pi square alpha beta m n sin m pi xi by a sin n pi eta by b sin m pi alpha by 2 a sin n pi beta by 2 b. So, you get q m n and hence a m n is found out. So, a m n you can see 16 p and some q m n. So, 16 p q m n is this function. So, 4 into 4 was there. So, 16 is there, and a b will get cancelled. So, ultimately we are getting that 16 p divided by pi to the power 6 alpha beta m n into d m square by a square plus n square by b square whole square, and this f the function of xi eta alpha beta. Xi eta are the coordinates of the center of the load, centroid of the load, and alpha beta are the dimension of the load. So, this function I have written separately, so that this function is now this. So, alpha f function of xi eta alpha beta is now sin m pi xi by a sin n pi eta by b sin m pi alpha by 2 a sin n pi beta by 2 b. So, knowing this function we can completely know the a m n, and then this q m n and other quantity can be calculated. Okay. So, I am giving a self assessment problem, just application of this theory, partially distributed load and Navier's method. Partially distributed load are sometimes very useful, especially for bridge deck design. So, bridge deck consists of wheel load, and wheel load may not be fully distributed over the deck slab panel. So, contact area, it is distributed only on the contact area, tire contact area, and different contact area specified in the codes of provisions, codes of practice in different countries. So, here I am taking an arbitrary contact area, say 0.5 meter by 0.75 meter, just to illustrate the process, and the total load I have taken as P equal to 300 kilonewton. And for example, this is a panel of the bridge deck 4 meter by 3 meter, simply supported along all edges, and concrete slab we take the grade of concrete as M25, and whose characteristic strength is 25 Newton per millimeter square. Poisson ratio of concrete is assumed is 0.2. So, loaded area is 0.5 cross 0.75 and total load is 300 kilonewton. So, solution is obtained. I am giving some important hints. You can complete and compare the results with the results given here. Okay. So, A is equal to 3 meter, B is equal to 4 meter, and alpha is equal to 0.5, beta is equal to 0.75. Load is placed symmetrically with respect to center. So, our xi, that is the x coordinate of the centroid of the load is 1.5 meter and y coordinate of the centroid of the load is 2 meter. Modulus of elasticity, because in this problem only this characteristic strength, that is grade of concrete is given. Now, based on the grade of concrete, say M25 concrete is selected here. For M25 concrete, characteristic strength is 25 Newton per mm square. So, modulus of elasticity is given by this formula, Indian Standard Code. So, this is the empirical formula, we take the help of this formula to calculate the modulus of elasticity. So, modulus of elasticity is here 5000 into root FCK. So, it is calculated as 2.5 into 10 to the power 7 kilonewton per meter square, because this quantity is Newton per millimeter square. So, converted to the into kilonewton per meter square. Flexural rigidity D is coming out as 20098 kilonewton meter. So, expression for deflection is this 16 p sin m pi x sin n pi y by b, and this function f xi eta alpha beta, which contains the coordinates of the load, centroid of the load, and the dimension of the loaded area, and numerator contains this pi to the power 6 alpha beta, that are the dimensions of the loaded area, m n are the integers, and d is the flexural rigidity we have already computed here, and these functions are there, m square by a square plus n square by b square whole square. So, after substituting these values and carrying out this summation, we take here these two terms, two odd terms, say m is equal to 1 to 3 and n is equal to 1 to 3, and we have calculated this W max center deflection, because it is a symmetrical problem. Again the deflection will be maximum at the center, and bending moment in both the directions, say m x and m y direction, is calculated. In the x direction it is 56.49, in the y direction it is 43.61 kilonewton meter per meter. Remember one thing, that all the stress resultant, that is bending moment, shear force, S shear, whatever you twisting moment, all are expressed in their respective units per unit length of the plate. Okay. Suppose for example, bending moment unit is kilonewton meter. So, it has to be expressed as kilonewton meter per meter. Okay. So, let us summarize what we have done in today's class. In today's lecture, we have outlined an exact solution of the plate equation, where the plate is simply supported all along the 4 edges. So, actually Navier's method is an exact solution, and it is a very well known analytical method used everywhere. Say when you take a composite plates or any other thing, this Navier series has to be taken for such a boundary condition, and simply supported boundary condition is very common, and it provides the benchmark result for various complicated problems. So, therefore, this problem that we have discussed today's class has significant impact on various other results that we will obtain in future or will be used in research project. So, in this lecture we have outlined this exact solution. Navier's method is used, and it is characterized by double trigonometrical series, and the method is illustrated by a simply supported rectangular plate with uniformly distributed loading and also partially uniformly distributed loading. The convergence of the series has been tested for deflection and bending moment, and it is concluded that for deflection the convergence is rapid in case of Navier's method. Only first term gives reasonably accurate results. The corner reaction force along simply supported edge is also discussed, and lastly an exercise, a self assessment problem based on Navier's method is given for solution. So, you can solve the problem and compare the results with the results that have been given in the slides. Okay, thank you very much.